So hello everyone, thank you all for being here today, especially before the Chandra deadline next week, so we appreciate it. Our first speaker will be Jordy Develaar.
Thank you.
So he's a postdoc research fellow at Columbia University and the Flatiron Institute Center for Computational Astrophysics. And he obtained his PhD from Radboud University in the Netherlands and is a member of the EHT collaboration and an associate member of the LISA consortium. So his primary research focus is modeling the emission produced in the accretion flows of supermassive black holes. And to this end, he combines high performance computing magnetofluid simulations with radiation transfer methods. And his work on black hole accretion flows is used to interpret millimeter, near infrared, and radio observations. And more recently, he started developing binary black hole models aiming to predict electromagnetic signatures of laser interferometer space antenna targets with Chandra, XMM, and Athena. So welcome, the floor is yours.
Thank you so much for the kind invitation, and thank you all for attending my talk. So today we'll be talking about one of the most energetic events in the universe since the Big Bang, namely the highest one of massive black hole binary merger. So what are these? So we expect that black hole binaries reside in numerous galactic nuclei. As two galaxies merge, we think both of them have their own supermassive black hole, and due to tidal interactions with like stars and the gas in the galaxy that forms after the merger, we think these two black holes will sink towards the center and eventually will start to orbit each other and emit gravitational wave signals. So these gravitational wave signals are hopefully a thing that LISA will measure in like 10 to 15 years from now, and they expect to measure hundreds of these up to a redshift of 30, so very deep into the universe. One very important aspect of all of this is that LISA has a pretty large field of view, and within this field of view there are like 1,000 AGN. So if you want to figure out which galaxy is actually producing the gravitational wave signal, to measure them. And for this, people are aiming to use electromagnetic signatures and then look for a very clear telltale signature that will tell us if there is indeed a binary there or not. And why do we want to know where these binaries are? Well, binaries are crucial for our understanding of how their host galaxy evolves. Like it's such an energetic event, and it steers up like a lot of the galaxy's properties. So how does this affect star forming? How does this respect the overall structure and material content of the AGN? What happens with feedback, etc. So we want to try to pin down like how a binary affects its host. And additionally, an electromagnetic signature and knowing where it is and what redshift and at what distance, this can also be like a standard candle for doing cosmological measurements, specifically measuring, for example, the Hubble constant. And as many of you might know, there's of course this tension in the Hubble constant currently, and LISA hopes to help lift the tension that is currently there with like local measurements of the Hubble constant and like far out measurements of the Hubble constant. So to understand the electromagnetic signatures, we have to understand how the direct environment of a massive black hole binary looks like. And this is quite different from, say, a stellar mass binary, which we think typically merges in a very clean vacuum-like surrounding, and there's not really an electromagnetic signature coming out of them. So how is this different? Well, you have the massive AGN disk around the system, which surrounds the binary. So let's see, does this pointer work? It does not. Now it does. So you have like a large disk sitting around the binary, which is here in the center. You have like all kind of substructure in like a large cavity that has been carved out as the binary rotates around. There's matter being transferred from the circumbinary disk onto two smaller disks. Each black hole has one, which we call a mini disk. And some of the material is flung out as the binaries accrete, which deposits themselves in the far end of this circumbinary cavity. And this is also what makes this cavity very asymmetric. So you have like angular momentum that swings there, and that is stored here at the inner edge, and therefore the cavity is not like a nice symmetric system, but more like an elliptical system. So again, mini disks, you have these streams going outwards, and the circumbinary disk here. And all of these things have their own electromagnetic signals that they can potentially produce. So how many do we how many do we already have in our observational samples? So currently we think that there are like 150 candidates. These are typically found with like large time domain surveys in the optical. If you look at the population, they're typically more biased towards like the higher mass range, so like 10 to the 9 solar mass. They have orbits of a year or more, and they get detected via Doppler modulations in their light curve. So here's an example of PG 1302. So you have like the data points, it's like the error bars here, and if you squeeze your eyes a little bit, you can see that there is some periodic perturbation on it, which people attribute to the binary motion. So as the binary as one of the components moves towards or away from you, it will either boost or deboost the signal that we measure. However, there is a catch here, and it is single black holes are perfect binary mimickers for like 1 or 2 orbits. And this is because of the way that quasars generate their variability in their disk. It's a red noise spectrum, and therefore you can have a light curve that mimics a periodic signal for like 1 or 2 periods. So this was like stressed out by Graham et al. 2015 and Vaughan, and they have like this really nice comparison. Also, this is PG 1302, the same source that I showed earlier. So the top one is a fit of like a binary signal. So you see it like nicely follows the black dots, but the bottom 2 here are red noise single black hole damped random walk signal. So this like pinkish line like equally well fits the data as this red line. So this is not a very conclusive test to just look for like sinusoidal patterns if you only have such a short amount of observations. As a second mechanism, and this is my favorite binary candidate, it's called Spiky, or it was dubbed Spiky. It was found in the Kepler field of view in 2010. It has a sawtooth pattern, like on the longer time scales. This is attributed to an eccentric binary. So the orbit is not perfectly circular, but eccentric. This means that the velocity along the line of sight changes in a slightly different way than a nice sinusoidal pattern. And on top of that, there's this reason why people call it spiky. There's like this massive amplification here at the moment where you expect that the binaries align with each other along the line of sight, because here like your velocity amplification goes to 0, like your magnification is 1. So there's no along the line of sight motion anymore. So what happens here, people interpret this as a gravitational lensing event where the foreground black hole lenses the emission of the background black hole, and you get a very steep amount of increased luminosity as an observer far out. So in the literature, this has been studied, these self-lensing flares, but what people typically do for studying them is that they use a microlensing approximation. This is nice because it's analytical, so you can do a very large parameter study without too much computational cost. However, like a microlensing, it typically uses point sources. There's not a real black hole image in there that has all the nice attributes that a black hole can create. You don't have any strong gravity effects from the very strong curved space-time. So there are a lot of questions we had, like how well does this approximation actually work, and what kind of features are we missing if you take this microlensing approximation. So our goal for this work was to study these self-lensing flares, but then use a general relativistic ray tracing code. And a general relativistic ray tracing code is a code that integrates geodesic equations in curved spacetime, so it takes GR into account. It has a camera somewhere far out from a region of interest. You start integrating these geodesic equations, and along the geodesics, you solve the radiation transport equation to to measure the amount of emission that ends up on the camera. So we did this with a code called Raptor. This is a ray tracing code that I co-developed during my PhD, and that has been used extensively within the context of the Event Horizon Telescope. So this was a single black hole code. And when I started working at Columbia, Zoltan Heyman was like, what about 2 black holes? Can you do 2? So, well, I had to prepare for some trouble there and make a double, but it was quite a challenge. I implemented an approximate binary metric to describe the spacetime of 2 black holes, and I put them on Keplerian orbits. And the richness of this problem is that all of a sudden you have an incredible amount of extra model parameters that you can start playing around with. So I started varying the mass of the black holes and the mass of one component over the other. You can start changing the spin between the 2 black holes or have no spin at all, and the inclination of the spins. There's like the orbital separation that you can alter, the inclination of the binary as a whole, the mass accretion rate in the respective disks around the black hole, and set the eccentricity as well. So there's like a whole slew of models that I generated, and unfortunately 20 minutes is not enough to talk about all of them, so I'll just try to highlight my most important result in this talk. So a good thing to keep in mind is that for this model, I used semi-analytical prescriptions of the accretion disk around the mini disks. I do not have a circumbinary disk at larger scale. This is just the 2 mini disks, and I describe them with a Sokurov-Sunyaev thin disk. So this is all like an analytical prescription. There's no time variability whatsoever. To give an example of how like these Sokurov-Sunyaev style disks look like, I borrowed a nice visualization by Jeremy Sneakman from NASA Goddard of a single black hole, which nicely highlights the features that you will also start to see in my simulation. So you have like this accretion disk here in the front. There's the emission above and below the black hole, which is here in the center. This is lensed emission. So this is just the emission that comes from behind the black hole itself. The darkening in here in the center is somewhat similar to what we find in the UHT, and this is due to the event horizon that is gravitationally lensed. So this is what we typically call the black hole shadow, which is the geometrical cross-section of the black hole. So light rays that will go towards the black hole are captured, and there's no light emitted outwards. And here you see a photon ring, which is a critical curve where photons are able to circle around the black hole for many, many times. And that is what's generating like a higher amount of emission compared to outside or inside of this ring. And then one additional part is if you start moving this disk around, you can see that the left side is brighter than the right side because of Doppler boosting. So what if you then, instead of 1, grab 2 and you start orbiting each other? So this is one of my models. It's at a viewing angle of 87 degrees. So it's close to edge on, with 90 meaning perfectly edge on and 0 meaning perfectly phase on. It's a binary separation of like 100 gravitational radii. It's an equal mass binary. It's an optically thick model, and this is in an X-ray band. It's like 1 keV. So now we start rotating these black holes around, and you will see that as soon as they start to line up, you get like this, like the background one just hugs around the foreground one and like goes around the Einstein ring, forms an Einstein ring, and here it does it again. So this, of course, looks nice and pretty, and if you stare too long, then you get quite zen. But what kind of science can we do with this? Because we're never going to measure a black hole binary at this separation in a far out universe. The EHT is not good enough for that. You can't have an X-ray imager that gets to these incredibly high, close in high resolution to measure this. So we have to look into another aspect of this, namely what can a light curve tell us? What does the photometric signal look like? So this is a 90 degrees model. So this is perfectly edge on, same binary separation, also equal mass, again in the 1 keV band. But now here on the bottom, I also slow the normalized flux as a function of time. And twice in this orbit, when the black holes align, you see that there is a massive increase in the amount of emission that my code measures. And additionally, there's another very intriguing feature that wasn't being seen in these microlensing studies before because they were using point sources. And the source didn't have any morphology that you can probe. Well, what happens if you put a ring behind a lens? Well, if you have like a looking glass and you go over a ring-like feature, the left side is bright, so it amplifies. then the focal point hits the black hole shadow, which is darker. So there's nothing to amplify there. On the right side, you find this ring again, and there's amplification again. So the amplification probes the substructure of the accretion disk in the back, and therefore imprints some of that information into the light curve. And you see that the light curve goes up, it goes down a little bit, it goes up and goes down. And the point where it is exactly at its lowest is here in figure 3, where you have a perfect circle around the foreground black hole, which means that there is perfect alignment between the foreground and the background black hole. So I found this quite interesting because as an EDC scientist, it was, wait, what? Can we actually maybe measure like the black hole shadow with how wide this separation is? And like the separation of the beginning of this dipping feature and the end of this dipping feature is set by the size of the image that you are probing. And given that the black hole shadow is something that is constrained by GR, so if you know the mass of the black hole and the amount of spin of the black hole, you know how large it should be. And the mass of the black hole, in the case of a black hole binary, is tightly constrained by the modulation of the signal. So you can lift the degeneracy of the mass with respect to the duration of the peak and fold those two together to see if it matches with what GR would predict. And what is great by this is that you don't need VLBI to do this. Like EHT currently can at most like measure 2 shadows. Well, this doesn't really depend on the spatial resolution, but more on like how bright the sources are. So this opens up a potential new way of measuring black hole shadows throughout the universe. But there are, of course, a lot of caveats as well. So first of all, how are we going to find this dip and what are the probabilities? Because as I said, like you have to be close to edge on, like how close to edge on, and what are your percentages then? And is that not like a very small chance of actually measuring them? So we did a little bit of a back to the envelope estimate. Like if we take the typical current data, 10 to the 9 solar mass black holes on periods of typically a year, this dip would last for a few days. And the inclination window, we did an inclination study in our paper as well to see how tight the window should be for that subset. And then you're talking about like a couple of degrees at most that you can actually see a dipping feature. So assuming like a uniform distribution of the binaries on the sky, which is I think very reasonable, you find a probability for finding this in the current data of like 1%, which is not that bad. Like we have like 150 sources, 1%, maybe there is one. And additionally, we can of course also think about like what other sources can we start probing. And for this, like the Vera-Rubin Observatory is I think going to play a crucial role because the LSST survey is going to probe 100 million AGN targets. And it's coming online next year. So hopefully we will find some new black hole binary candidates there that potentially also have like the self-lensing feature in them. And then a next channel is of course to look at pre-merger electromagnetic emission of LISA sources, because if we know that there are pre-merger and creating gravitational waves, we know that there are black hole binaries there already, and then additionally we can look also for the self-lensing in like a tighter system. But yeah, there are then of course, as we realized when we were writing the paper, like a lot of other caveats that we try to resolve in the years after that. So a couple I have written down here, of course, as I said, like the analytical prescription for the disks is not very realistic, right? First of all, I'm using a Sukurov-Sunyaev disk model, which was developed for like single AGN, and I'm talking about double AGN here. And there are like streams and shock heating and all kind of other additional variability that is not captured by such a model. I don't have these competing effects, like the streams can generate shocks. There can be shocks between the 2 black hole binary disks. I don't have this larger circumbinary disk. My analytical pseudo-Keplerian velocity profile of my tiny accretion flows is also like, yeah, I had to make a couple of shortcuts here to make this project feasible, but how do these choices change my result? So for this, I teamed up with Luke Krauf. He's a graduate student of mine, working together with Professor Heyman at Columbia University, and he's an expert in hydrodynamical simulations of these binary black holes. And for that, he uses a 2-dimensional vertically integrated GPU code called Silphage. This is a public code, so if you ever want to try to run some simulations yourself, Here's the GitHub for that. And what this code does, it solves the hydrodynamics equations by using our gamma law equation of state. So what this means is that we also get temperatures. It's not just an isothermal simulation. We have an explicit viscosity in there that we can change. We picked a mass of 10 to the 6 solar mass, which is right into LISA most sensitive band. And we took a separation radius similar to the model that I just showed. And this is of course great because this will give you mass accretion rate variability, streams, etc. So the question then was, do we still see this feature or does it disappear? Because now we have a temperature profile due to shock heating and other effects. The velocity profile is shown to be not necessarily Keplerian anymore. This circumbinary disk can actually block the view. So here I show a snapshot of the simulation. If we post-process it with our ray tracing code, you can see that there's like this darkness in the front and you can actually not see the binary anymore. And the accretion variability should alter the light curve. So we coupled the output of his simulation to my ray tracing code, used the same binary metric as I developed before, but now with like this more time varying accretion flow. And the nice thing is, if I press play here, you will see that this right black hole will start to move to the left, and it will start to generate very similar patterns as you saw in my more simplified model. And if you look here on the bottom, this is the light curve as a function of time. You see that there is 2 peaks in here. One has some competition. There's a lot of like additional noise here. This is because of these streams are interacting and shocking and giving additional variability that is not captured by my model. But this more cleaner pass by actually gives you like a double peaked structure where the width of this structure is again set by the black hole shadow. And this is just over one orbit. What we also showed is that if you use phase folding, and if you have a feeling about what the periodicity is, you start to average out all of the noise here, and this peak will also start to look like the first peak that we have over here to gain a higher signal to noise ratio. And an interesting finding was as well that the circumbinary disk that blocks, we first thought this is a competition, it's a foe, right? It's going to be, we will not be able to look into there. But given that what we didn't take into account is like the lensing actually boosts the emission higher up. So it's not necessarily a foe, it's more of a friend because it blocks the variability very close to the horizon and the variability caused by these streams, while it still allows you to see emission higher up because of the lensing of the system as a whole. So it turned out to be a friend. An additional thing that we then did with the same set of simulations is like, well, if we can run simulations at a fixed orbital separation, we can also start merging them. So we started merging these 2 black holes together and as you can see here, they get closer and closer and closer. The amount, this is by the way, the surface density of the accretion disks. So here it's yellow, here it starts to become pink. And as you get towards the merger, they actually disappear. So one quick final result that I want to highlight is that as the merger happens, you start to starve the black holes mini disks. And as you starve them and there's no accretion happening anymore, what actually happens is that the X-ray emission, which is mostly the thermal X-ray emission, which is predominantly produced by these mini disks, also disappears. So in the initial phase, the X-ray is the green line here. There's like a lot of X-ray emission for this specific model, like 10 to the 44 ergs per second for like this 10 to the 6 solar mass system. And as you get closer and closer to merger, you'll see that they start to go faster and faster. You get more and more of these streams. The density goes down. The temperature will start to change. The disks will start to become smaller and smaller as they start to getting starved. And here, all of a sudden, at merger itself, the X-ray emission drops by almost 5 orders of magnitude, the thermal X-ray. And this is great because this is a telltale signature for X-ray emissions that can work together with LISA. Like you only need like 2 data points. You want a data point for when it wasn't merging yet and 1 data point after it was merging, and then try to see like, do we indeed see such a steep decline within the LISA field of view. So with that being said, I will leave my summary and outlook up, and I'm happy to take any questions.
Thank you. Do we have questions?
Anyway, I'm loud, I think. I guess for people online,
Hello. That's working.
All right, so this additions are really, really nice, and I'm wondering, I mean, of course, there's extra structure on top of just the circumbinary disk, right? There's going to be the broadline regions, the clouds, and so I'm wondering how that's going to affect this, probably negatively, the accomplishment.
Yeah.
The other thing which I think might be interesting is that, you know, that X-ray dip reminds me of one of the changing state AGN that was found recently, 1ES, whatever it is.
Yeah.
It would be interesting to actually look at that in more detail and see if you could explain what was going on with something like this.
Yeah. Yeah, I was made aware of this by Matteo Bonetti from, we worked with Aaron Cara. He was also pointing me at that specific source. He said, well, such a weird changing look AGN, no one really understands what's happening.
Exactly.
And then he saw this talk, he was like, wait, that looks awfully familiar. Yeah. Thank you.
Questions? Do we have any questions? Yeah. Oh, is this good? Yeah, but is it unmuted? Yeah, Jen, go ahead.
Yeah, so that's an excellent talk. Thank you. And this isn't the fair question necessarily, but lots of AGNs, or maybe 10%, have radio emission, radio jets, X-ray jets, and how would all that fit into it, and what might happen to them as the black holes merge, and can Lisa actually see 10 to the 9th solar mass black hole mergers?
Yeah, great question. Lisa is not able to see 10 to the 9th solar mass. The model that I showed for the merging black hole was at 10 to the 6th solar mass because it's perfectly then at the peak of the sensitivity from Lisa. And your first question about the jets, that one I'm very excited about. Because as you start the accretion disk, you just will have like a monopole-like magnetic field structure that you still have to get rid of, because there's still probably a jet on these two binary black holes. So as I said, like the thermal X-ray will dip, but I'm fairly certain that the non-thermal X-ray will actually start to rise, because you need to dissipate away this magnetic field that is still there. You get like a balding black hole remnant that will rapidly increase in non-thermal X-ray emission. For that, like the binary code that we used was purely hydro, so no magnetic fields yet. But what I'm working on with Matthew Liska was a fellow here at Harvard and now at Georgia Tech with his hammer code. We're implementing a black hole binary in there to study this system in its full richness with black hole spin, and have the jets popping out of there as well, to study how the jet morphologies change as the binary is migrating inwards.
So that's very exciting. I'm assuming then we might be able to see these things even before Lisa.
I hope so.
So we are sort of like on time now, but feel free to, we have, I think, lots of time slots to meet with the speaker, so thank you again. So while they set up here, our next speaker will be talking about using high resolution X-ray spectroscopy to unveil fundamental physics. So we'll be hearing from Julia. She's a final year PhD student at the Institute of Astronomy at the University of Cambridge. And she's been working with Professor Chris Reynolds and James Matthews, who are now based in Maryland, since 2020. And her focus is on understanding how we can use current and future X-ray telescopes to constrain physics beyond the standard model and the spin of accretion of accreting black holes. So, Julia, with this very short introduction, the floor is yours. Let me see if we can see your screen fine.
Can you hear me and see my slides?
Yes.
Okay, perfect.
Okay, go ahead.
Okay. Yeah, so thank you very much for the introduction, and thank you for inviting me. Yeah, so today I'm very happy to be able to tell you about my thesis work, which is due at the end of the month. So hopefully I'll be able to convince you that some of the work that I've been doing is interesting. And sorry, I think I'm just having trouble changing slides now. Yeah, so before I start, I just wanted to mention that I'm broadly interested in the 3 research areas that I've listed here. So black holes, physics beyond the standard model, and extragalactic astrophysics. So if you want to discuss any of these with me or any other research area, please do sign up to speak in the spreadsheet. But yeah, so today I'll be talking about my work on axions and on supermassive black hole spins. So I've written 4 papers on these topics, and I'll be mostly spending time discussing my axiom work. So at the beginning, I'll talk a little bit about physics beyond the standard model, and then I'll talk about why axions are important and how we can study them or constrain them using X-ray observatories. And then I'll talk about the implications of this work for frameworks that predict the existence of axions, as well as some possible future directions. And then for the second part of my talk, I'll be discussing how we can use X-ray observations of accreting supermassive black holes to set constraints on spins of black holes. And then I'll be talking about my current project, where I'm trying to build a model describing the observed distribution of supermassive black hole spin set from X-ray reflection. So this will hopefully tie in a little bit with the previous talk. Okay, so for the first part of the talk, I'll be discussing my work on axions. And before getting into the details, I just want to highlight that we all agree that the standard model of particle physics is extremely successful at describing a wide range of phenomena that we see in nature, but it's still missing some things. So the first one, and perhaps the most obvious one, is that we don't have any non-baryonic candidates for dark matter. And we also have the dark energy problem and something called the strong CP problem, which I'll describe in the next slide. So all of these things are tensions that axions could provide solutions to in principle. And there are many physics beyond the standard model theories that offer solutions to these tensions. And the key reason why the axiom constraints that I'll present are relevant are for the string compactifications or string theories that predict the existence of these particles. Okay, so I want to spend a little bit of time describing the first type of axions. So you may have heard of the quantum chromodynamic axion or the QCD axion that was proposed in the 1970s, and the fact that this particle was named after a cleaning detergent. And this is because this particle was proposed to solve the strong CP problem in particle physics. So this is the absence of charge parity violation in the strong sector. So by the strong nuclear force that we see in nature that clashes with the predictions of the standard model of particle physics. So the easiest way to solve this tension that was proposed in the 1970s is by introducing a new symmetry in the standard model Lagrangian. And as you may remember from Noether's theorem, when we get new symmetries and they break, we get new particles. And the potential associated with the axion field is governed by the axion mass. So for this QCD axion, the original axion, the physics of these particles and the way it interacts with particles in the standard model, such as photons, are governed by the axion mass and this global decay constant, which are well constrained by the theory. But the type of particles that I'll be speaking about today are called axion-like particles, and I'm just going to refer to them as axions for simplicity from now on. And they are model-independent generalizations of the QCD axion, in the sense that their masses and couplings are no longer constrained by the theory. And in general, they do not solve the strong CP problem. And you may know, and as I have mentioned, that some axion models are very compelling dark matter candidates. And if this is the case, the phenomenology of these particles will be governed by the axion mass. But the X-ray constraints that I'll be presenting hold regardless of whether axions are dark matter or not. And the important thing here is that the phenomenology of the interaction of axions are the same as for the QCD axion. So here, M and F, so the mass and the decay constant, are no longer constrained by the theory. And we'll be talking about a regime where this F is governed by the photon axion interaction, whose strength is underpinned by this coupling constant G. So as you can see here, these are predictions for this parameter G for different string theories, each encoded by a different color. And here we can see that the X-ray constraints that we can infer from Chandra, and these are projections from Strobeck's, are already starting to probe these realms of string theories and could potentially constrain them, which is very exciting. So the way in which we are going to be trying to constrain or find axions is through their interaction with electromagnetism. So if we look at this Feynman diagram here, what this is telling us is that if we have a photon beam that is propagating or traveling through a magnetized medium, then in principle, photons can undergo conversion into axions. And as we can see, this interaction will induce energy-dependent distortions or wiggles, whose amplitude will increase with the energy of the beam. But for a given energy, we also get distortions with the path length traveled by the photon beam as it's traveling through this magnetized medium. So what we want to do is to use astrophysical sources to look for these energy-dependent distortions. And if we don't see them, then this means we can study or constrain axions. And I want to highlight that the ICM, so this is the gas that is permeating galaxy clusters, is an extremely compelling source to look for these distortions. Because at X-ray energies and at sufficiently low axion masses, so here we'll be talking about 10 to the minus 12 EV and masses below that, the photon axion mixing probability, so this oscillatory function that I showed in the previous slide, scales as the dot product, or sorry, just the product of the magnetic field and the coherence length of the magnetic field in the ICM. And we know that in the cores of the richest clusters of galaxies, so cool core clusters, the ICM can reach up to tens of microgauss, and it's characterized by coherence lengths of 100 kiloparsecs. So it turns out that this function is, or this number, sorry, is quite high in galaxy clusters or in the ICM compared to other astrophysical sources. So the process that I'll be, or the constraints that I'll be presenting are relevant if we think about an AGN that is hosted at the center of a rich galaxy cluster, and the X-ray emission of the AGN is traveling through the magnetized cluster line of sight. And as this process is happening, photon axion interconversion will induce energy-dependent distortions in the spectrum of this AGN. So if we don't see them, this means that we can constrain axion parameter space. And as you can see, this has been used not only with the ICM, but with other astrophysical magnetic fields. So this is a so-called exclusion curve, where here I'm plotting constraints from many different studies, and we interpret it as follows. So if we take a shaded region, for example, the results from CAST at masses 10 to the minus 12 eV, then everything above the curve or this region is parameter space or values of G that are excluded for that axion mass. So you can see how different laboratory experiments that I plot in red here compare to astrophysical bounds, which are plotted in green. So this is a key parameter that we want to constrain, the photon axion coupling constant. And you can see that our limits from Chandra are the tightest or the most stringent to date at these low axion masses, which are the most relevant or could be relevant for these string theories that I was mentioning. And then we also have projections from Athena telling us that Athena will be able to improve on these constraints. And I just want to mention that you can think analogously to these axion oscillations by thinking about neutrino flavor oscillations, with the axion here being a third polarization state of the photon beam. Okay, so now I want to present the results from where these constraints, Chandra constraints, come from. So to infer these constraints, we use very luminous radio quiet quasar that is sitting at the center of a cool core cluster, and it's an extremely interesting object. So this is H1821 because Compton cooling by the quasar radiation is thought to dominate in the inner 10 kiloparsecs of the cluster core. And in particular, we use archival Chandra grating observations of this object. And here you can see one of the images that we used. And you can see that the quasar is extremely bright compared to anything in its surroundings. And the use of the grating data enabled an extremely high quality extraction of the intrinsic emission of the AGN, free from contamination of the cluster emission, as well as photon pileup. So we had a lot of photons, and we had a very clear view of the AGN emission. Sorry, I'm having trouble changing again now. So here on the left, you can see our best field model for the quasar spectrum. On the top panel, and then on the bottom panel, you can see our energy-dependent residuals resulting from fitting this model to the spectral data. So the ultimate question that we wanted to ask ourselves is whether photon axion distortions or interactions could describe these energy-dependent residuals. And to do this, we had to build a library of photon axion mixing models and fit them to the original spectrum, and then compare their goodness of fit compared to that of the astrophysics best fit model to infer constraints on axion parameters or posteriors on axions. And I just want to spend a few moments talking about the magnetic field assumptions. So again, 20 minutes is not a lot of time to go into the details, but if you're interested, please do check James Matthews' paper, because it contains a lot of discussions about the assumptions that we make on the magnetic field. So it turns out that when we build these photon axion mixing models, our signal is very, very sensitive to the turbulent structure of the ICM along the line of sight. And here you can see an example. So each of these dashed dotted and solid black lines are showing predictions for the photon axion mixing probability for two different orientations of the magnetic field. And both of these predict or reproduce the expected field profile in the host cluster, which is shown by this orange curve here. So what we did essentially was to build this library of photon axion mixing models for possible orientations of the magnetic field. And then we marginalized over these parameter because, as you know, probing the very detailed structure of the ICM from observations is very challenging. And we know that the assumptions that we make on the magnetic field are the most limiting in terms of the coupling constant on axions that we infer. But we know that they produce a systematic shift. And in a way, we are being conservative because of, and this was demonstrated by some recent work. And I'm happy to provide more details. But yeah, so these are the leading constraints on axions. So here we have zoomed in onto the previous plot that I was showing. And I just want to highlight that the future of this type of work is bright with upcoming X-ray observatories. So here I have listed a few of the pro-class concepts given their improvement in collecting area and spatial and spectral resolution. And in particular, we are very excited about Athena because Physics Beyond the Standard Model is one of Athena's topical panels. And in fact, we were able to show that even when considering the possible effects of detector miscalibration, which induces energy-dependent residuals, then Athena will be able to recover most of its projected sensitivity to constraining axions if we use machine learning techniques to circumvent these effects. So with machine learning, we can build a neural network that is able to distinguish miscalibration or energy-dependent effects induced by systematic uncertainties or miscalibrations from those of axion signatures. And in terms of the implication that this has for the string theories that I mentioned before, this was explicitly shown in a work by Naomi Chandler and collaborators. But here you can see that our X-ray constraints, which are shown by this line here, seem to be in tension with some string theory models. So here, this distribution of G effective is somehow related to the photon axion coupling term that we are constraining with our Chandra or X-ray observations, and H is the number of axions being produced by each of these string theories. So this is incredibly exciting because we could be constraining already some of these string theory models, but there's still a lot of work being devoted to trying to match and understand how we can use our constraints to inform these frameworks. And in terms of what I think we should be looking at for the future, I think a very relevant and exciting direction is to revisit our magnetic field models that predict these photon axion signatures in galaxy clusters. And this is because recent work by Pierluca Carenza and collaborators showed that if we use MHD simulations to make these predictions by using the full three-dimensional structure of the ICM, then photon axion, the characteristic photon axion signatures seem to be a little bit different to those that we predict with the simplified models of the magnetic field that I was mentioning before. So refining our predictions has to be done if we want to confirm whether we have missed anything when comparing models to data. And then we need to use these new models and these more consistent models to check the data that we already have. And I think a very compelling direction with which we could do this is to use MHD simulations of galaxy clusters. Okay, and now I just want to move on to my second area of research that I'll discuss today, which is how we can use X-ray spectra of AGNs to constrain supermassive black hole spin. So I'm interested in spin because it's one of the two fundamental properties of astrophysical black holes.
Julia,
Yes.
excuse me, can you hear me?
Yes.
Just this morning, 2-3 minutes. Can you?
Yeah, sure. Yes. I'll just mention that Yeah, the principle of this method is that the disk is ionized and it produces these X-ray reflection features from the primary continuum, and a very compelling indicator of these relativistic reflection coming from the innermost regions of the disk is the relativistically broadened INK alpha line. And we did this type of study by looking at the spectrum of H1821, which is the very luminous quasar that I was mentioning before. And because the observations that we used in the previous work had been taken at 3 weeks apart, what we did was to use MCMC to study the parameter space enabled by relativistic reflection in both observation and epochs. And then we combined the outputs of these MCMCs to constrain the spin of the supermassive black hole. So this is very interesting because this is a very high mass black hole, so of mass 10 to the 9 to 10 to the 10 solar masses. But also when considered amongst the population of supermassive black holes whose spin we have constrained using these methods. So I just want to spend 1 minute, hopefully, if I have time, talking about my current work. So this is the population of supermassive black hole spins observed with X-ray reflection. So if we look at this plot carefully, we will notice that we are missing a lot of data, especially at the high masses. But there seems to be a cluster of points or sources here whose spins are quite high compared to these higher mass sources, which seem to be approaching more moderate spins. So if we match this with predictions of semi-analytic models and numerical simulations, it seems that these sources could be powered by coherent accretion, whereas these ones could be powered by incoherent accretion or mergers with smaller mass black holes. So what I'm trying to do now is to build a Bayesian model to see whether we can test this hypothesis given the data. And for this, we are taking into account different spin-dependent effects that affect our interpretation of these observed distribution. So yeah, hopefully I have convinced you that using the hot and energetic X-ray universe is very interesting if we want to study the evolution of supermassive black holes and physics beyond the standard model. And sorry for overrunning. I'm happy to take any questions.
Thank you so much. Do we have any question from in person people? It's certainly a topic where we all have a lot to learn here. Yeah, one.
Hi, what about X-ray polarization with XP? Is that a viable second mechanism to probe axions? Is there a polarization feature that you could use as well there?
I'm really sorry. I think I have missed some words. I think the sound is not very good. I'm really sorry.
The question was, can you use the polarization to constrain the
X-ray polarization.
yeah, from the XP.
From XP. Yeah, so excellent question. I think there's a group working on that, and I'm not involved, so I cannot provide any details, but there was a paper before XP was launched, showing that if you use polarization constraints, or sorry, polarization data from the Perseus cluster of galaxies, you can constrain axions, but you need very deep exposures if you use galaxy clusters as your target source of orders of megaseconds. But I believe they lie. So if I can go back, sorry, to the yeah, in between the 10 to the minus 12 to 10 to the minus 13 inverse GeV.
Okay, thanks. Any other question? No, I cannot see online. It's probably, sorry? You have one?
No, I don't.
Okay. So we have the schedule still, I think, with plenty of room for appointments. So if you have time or willing to discuss with Julia, please sign up. So with that, I think we are all done. Thanks a lot, Julia. Let's thank both speakers today. And see you next week.